All right, today we're diving into a really cool computational system called DCRE, and it's all built to answer a massive question, one that sits right at the heart of our digital world. How can you ever prove a computer is telling you the truth? I mean, think about it. We rely on computations we can't see every single day. The output from an AI, a financial transaction, even a digital vote. How do we really know that the process behind it was fair and that nobody tampered with it along the way? It turns out actually proving that is a seriously hard problem to solve. So let's look at how we usually try to solve this. You've got blockchain, which is secure, for sure, but it's just incredibly slow and inefficient because everyone has to agree on everything. Then you have audit logs, but that just means you have to trust the person or the system that's keeping the log. And what about so-called trusted hardware? Well, then you're just shifting your trust to the hardware manufacturer. You see the pattern here, right? Every single solution we have today just boils down to trusting something or someone. And this is exactly where DCRE just flips the entire script. Instead of trying to build a better system of trust, it asks a totally different question. What if proof had nothing to do with trust at all? What if it was simply about being able to perfectly, verifiably reconstruct what happened? And this is the core idea right here, proof by replay. It's actually pretty simple, but it's incredibly powerful. A claim, any claim, is only valid if someone else can take the exact same starting point, apply the exact same steps, and get the exact same result. That result gets locked into a unique cryptographic fingerprint. And if the fingerprints match, the proof is absolute. It's verification through reconstruction, not through trust. So, how does it actually work? Well, it's basically a four-step dance. First, you encode your data onto a starting grid. You can think of it like setting up the pieces on a chessboard. Then, that grid evolves based on a set of totally deterministic, unchangeable rules. Now, here's the really clever bit. The system doesn't record the whole board every time. It only records the changes, the deltas, from one step to the next. And finally, anyone can verify the whole game by just taking that initial setup and replaying those recorded changes. And this chart makes it super clear. On the left, you've got the original computation. It starts at state G0, does its thing, and spits out a final fingerprint. Let's call it F1. Now the verifier on the right starts with that same exact G0, but they don't have to rerun the whole complex computation. Nope. They just apply that simple list of recorded changes. If the fingerprint they generate, F2, is identical to F1, well, the proof is valid. It's a perfect match, or it's nothing. So where does all this action take place? It happens on something the source calls a lattice. And honestly, the easiest way to picture it is just as a fixed digital game board. It's got a set size, a boundary, and every single calculation happens right there, inside the cells of the board. The rules of the game are the same for everybody. Now, we get to the secret sauce, the thing that makes all this perfect predictability possible. It's called bounded arithmetic. And let me tell you, this is not how your calculator works. In DCRE, numbers don't overflow, they just wrap around, kind of like the hours on a clock. So if your system's limit is the number 9, and you calculate 8 plus 5, you don't get 13. You can't carry the 1. The result is simply 3. It sounds weird, I know, but this rule is absolutely crucial. It means a calculation in one cell can never spill over and affect its neighbors. And that's the key to making the whole system's evolution perfectly, flawlessly replayable. And because everything is so predictable, you get this incredible efficiency. Just look at the image on the left. That's what it would take to save the entire grid state. At every single step, it's a mountain of data. But DCRE does what's on the right. It uses what's called a sparse delta representation, which is just a fancy way of saying it only records the cells that actually changed. This makes the proof, the entire history of what happened, unbelievably small and easy to pass around. Okay, so this robust system for creating proofs, it unlocks something even more mind-bending. The source material puts it this way, with this really powerful quote: communication without triangulation, routing, or addresses. I mean, what could that even mean? Well, just look at this comparison. On one hand, you have basically all communication we've ever used. It requires a sender, a receiver, and a path between them. Your location and identity are essential. DCRE suggests something from a different universe. A message isn't a package sent from point A to point B. It's a perturbation, a specific pattern of changes you introduce to that shared lattice. Receivers aren't listening for your name, they're just watching the lattice evolve, and they recognize the unique evolving signature of the message itself. The source actually calls this the bowling alley metaphor, and it's perfect. First, you encode your message into a pattern. That's your bowling ball. Then, you inject it onto the shared lattice. That's you releasing the ball onto the lane. The whole system then evolves deterministically. That's the ball rolling perfectly down the lane. And finally, receivers who are watching that same lane recognize your message's signature as it travels. No addresses, no routing, just a shared lane and shared rules. So the obvious question, right? What happens if two people roll a bowling ball at the same time, or if someone tries to jam the lane? This might be the most incredible part of the whole thing. Thanks to that weird wraparound math, interference doesn't create noise or errors. The signals just combine. They create a new state that is still perfectly deterministic and perfectly replayable. A jamming attempt just becomes another verifiable part of the history. You literally can't break it. So let's just recap the huge advantages here. You get absolute verification with zero trust. The proofs themselves are tiny and efficient. It opens the door to a totally new kind of private, location-independent communication. And this core primitive gives you a rock-solid guarantee. For any digital process you can imagine, the same input will always produce the exact same verifiable output. So what can we actually do with this? Well, the potential applications are just staggering. Imagine being able to prove exactly why an AI made a certain decision, or a voting system where the entire election is a completely replayable, auditable history that anyone can check. You could guarantee where a product came from in a supply chain, build communication systems that are impossible to surveil, or even debug software by perfectly replaying the exact sequence of events that caused a crash. And that brings us to the final big thought here. DCRE proposes a world where proof isn't about trust or faith or believing some authority. It's just about the simple mathematical ability to reconstruct what happened. So it leaves us with this really powerful question to think about. If proof is just reconstruction, what else becomes possible?